In this video, what we're going to do is summarize a lot of the results that we have around the magnetic field and how it interacts with other charges, and also sort of how we deal with distributed currents, if you will. So one of the things that, again, we'll sort of emphasize here is that now we're interested in matter having charge. And instead of just charge, sticking around and creating an electric field, we're talking about moving charge. And so when a charge moves, it creates a magnetic field. So moving charge generates magnetic field. And that's a little bit different than what we had before because we were talking about static charges, charges that stayed still, they generate electric field. Now, it's true that a charge that is moving will have an electric field. It will also have a magnetic field. What we have done is we've sort of isolated the magnetic part of it and only talked about the magnetic part of it and sort of left the electric part of it separate from our conversation altogether. But know that we do have an electric field. It's just we're going to focus on the magnetic field that it generates. Now, when we started this, what we started with was a point charge that moved with some velocity. We'll say that it's moving in this direction. And then we're interested in sort of what's going on over here and what the magnetic field is that this charge produces. So the model that we have for a point charge magnetic field is mu naught over 4 pi, the charge itself, times the velocity that the charge has crossed into the unit vector that points to the location we're interested in, divided by r squared. So this is our point charge formula for a magnetic field. This is the magnetic field we would observe here due to this charge. Now, there's a condition here that we talked a little bit about very briefly, which is that the charge has to be moving slowly compared to the speed of light. So the way we often say that is that the velocity is much less than the speed of light. And the reason for that is electromagnetic radiation takes time to travel distances. It travels at a finite speed. So this model is useful under the condition that the charge is moving slowly compared to the speed of light, that we get information here very quickly compared to how quickly the charge moves to its next location. All right. Now, the nice thing about the magnetic field is that it also, like the electric field, obeys superposition. So if we have a bunch of charges, a whole collection of them, we can find the net magnetic field by simply adding up all of their contributions. So each individual charge might make a magnetic field, and we just add those up like we did with the electric field. Now, what we did in classes discussed, if you have a current that is a wire that has a bunch of charges moving, how does that actually work? Well, the way that we deal with that is by figuring out how to add up the magnetic field that is associated with a bunch of moving charges. And we use the exact same idea that we did for the electric field, namely that the little bit of magnetic field we get from a little piece of the wire, we can model it as a single sort of moving chunk of charge, just as we would normally do. And the idea is then we superpose all of the results. We add up all the pieces all the way along the wire, and we say, what's the total magnetic field associated with that? And so that is, in a sense, finding the integral by adding continuously this contribution. Now, we did a little bit of mathematical manipulation here to get this into an expression that makes a little bit more sense for this geometric shape. And the way we did that was by transferring the vector here onto the vector that points along the direction of the wire. And so the ultimate result that we get for some sort of wire like this was related to the current itself and the wire's geometry, which is that it's mu naught over 4 pi, and it's an integral of the current times a little bit of displacement that points along the current direction crossed into r hat over r squared. And so this was the Biot-Savart law. It was a way of describing the magnetic field associated with wires, in particular long wires. So we derived a result for a very long wire to determine that. Now, just like the electric field, this magnetic field can interact with charges, and it can cause them to be pushed or pulled around. But the interesting thing about the magnetic field is that it doesn't produce a force on a static charge. The charge that you are looking at that interacts with the magnetic field has to be moving. So if I have some current maybe like this, and I have a charge over here that happens to be moving, the magnetic field that this current produces at the location of this charge will interact with this moving charge. And it'll interact exactly like this, namely that this charge here, which we'll call Q, times its velocity, crossed into the magnetic field produced by this guy. So oftentimes what we do is we would refer to this as the test charge and the test velocity, and this is sort of the external magnetic field that is not due to this charge, but rather due to everything else that's around it. So what's curious about this is that it's quite a bit different than the electric field, right? If the charge itself is static, if it's not moving, it experiences no magnetic force. It has to be moving to experience that force, whereas when you have a charge that's just sitting still and there's some electric field, it will experience a push immediately. The other thing about this is that the direction of this force is given by the right-hand rule. So in fact, it is perpendicular to both the velocity and the magnetic field, meaning that all of these kinds of problems where we're looking at magnetic forces are fundamentally three-dimensional, right? The velocity and the magnetic field define sort of a plane, and the force is always going to be perpendicular to that plane. So we could have solved many electric field problems in 2 dimensions. This cross product forces us to work with these problems in 3 dimensions. Now, there's a couple of interesting things about this right-hand rule business. So if we have a wire with some current that's running down it, the right-hand rule tells us that the magnetic field will actually circulate around this wire. So current-carrying wires produce magnetic field that in this case will point into the board below it and out of the board above it. So if we were to sort of turn this wire vertically and look at it like this, what you get is you get currents that circulate around it. Sorry, not currents, magnetic field that circulate around it in these circles, right? And so all current-carrying wires have this property that produces these magnetic fields that go sort of around them, and it sort of dies off as you get farther away from it. What's important about that is that if you're looking at microelectronics systems, or you're looking at systems that are very sensitive to electromagnetic radiation, every one of these wires that you put in here is going to produce a magnetic field, and that might impact the other electronics. So it's important to think about this in general, because it could produce errant results in some kind of engineering problem that you might have. Now, the other thing that we have that's really cool about the magnetic field is that the way that it pushes charges around is such that it cannot increase or decrease the kinetic energy of a charge. It can only turn a charge around. So this makes it really useful for things like cyclotrons or mass spectrometers. Because what happens is if you have, let's say, a magnetic field that points into the board like this, and you send a charge in, let's say a positive charge that moves like this, the force that it's going to experience is going to be, in this case, pointed upward. So it'll get pushed a little bit. Its trajectory will turn just a little bit upward. And so at a later time, it'll still experience that same force kind of up and to the left in this case. And it'll continue on like that. The idea being is that the charge will actually orbit around this uniform magnetic field. It'll make a circular orbit. And so this results in uniform circular motion. Which means that the kinetic energy of the charge in question doesn't change. You can see maybe why that is. The force in this case is going to be perpendicular to the velocity. So at every point along any trajectory, it will turn it. But it can't actually speed it up or slow it down. You have to have an electric field to do that. This makes it really nice for constraining particles in a particular domain. The radius of that orbit, as we worked out in class, turns out to depend on the charge to mass ratio of the charge itself, which is really quite useful because in a mass spectrometer, for example in a chemistry lab, you can determine the charge to mass ratio of a sample by putting it in a magnetic field. So you can distinguish what kinds of material you have there based on how the particular particles or particulate matter actually turn in that magnetic